This is problem 6-20. It's on page 345. We're supposed to find the centroid of the area and the moment of inertia about that, or the second moment of area about the centroid through an axis. And it's not real clear, but what they really mean is a horizontal axis relative to the figure, despite the fact that we've got an axis of symmetry drawn vertically here. Just ignore that, except for the fact that it indicates that it's symmetrical. I've gone ahead and added a couple of highlighting rectangles on this. Now, let me pull them off so you can kind of see what the shape looks like. And let's start off with row 1 to see how I came up with the moment of inertia and the location of the centroid. Of course, the centroid's not going to be down here, right? It's going to be up here somewhere. It's on this axis of symmetry. But where? Well, we can find out with a spreadsheet. So the first thing I do is calculate the area of a rectangle. What rectangle is that? Well, it's 0.3 inches thick, 3 inches wide. And my scan's not perfect, so the lines are off just a little bit. But basically, it's that rectangle, that upper area. And this location of the centroid of that area, notice it's 2 inches up minus 0.15, minus half of 0.3 inches down. So that's 1.85 inches from the bottom of the feet, the bottom of those legs. And then the AIYI product is calculated here for that particular shape. And then I just went ahead and used 1/12 BH cubed. Easy enough. 3 inches wide, that's the base. 0.3 is the height. Cubed divided by 12. There we go. Now, then later on we'll go through the rest of this because we don't have the centroid of the area yet, and we need it in order to proceed. Let's go to the next area. And notice that area 2 and 3 are the same. What are those? Well, those are these areas right down here. One part of one leg without the triangular piece, and then this piece. Because understand, all we really care about is how the area is distributed away from the line at the bottom. Okay, that's all we really care about, not how it's distributed left and right. And that point will come into play very, very soon. So both part 2 and part 3 are a section of the legs. Okay, and so there's our AIYI product. I'll let you look at the details here. You should have seen enough rectangles by now to know that I'm going to calculate 1/12 BH cubed, and you can calculate the area of a rectangle pretty easily. So hopefully you see that the height of this is 1.7 inches. It's 0.3 inches wide. Pretty standard stuff so far, not all that hard. So that takes care of row 1, 2, and 3. But notice some area was missing, right? What about that triangular area? And what about this triangular area? How do I deal with that? Well, I used a trick. I realized that these two are symmetrical, so really they form an upside down triangle like this, right? A triangle that has the same length on each side. And so I was able, and by the way, it doesn't actually matter how the area is, that peak doesn't have to be isosceles. It could be at an angle. It doesn't really matter, because all we care about is how the area is distributed this way, not how it's distributed left and right, just vertically. So I use the equation for the moment of inertia of a triangle, and you notice it's the base of the triangle, which, remember, when these were over here, let's see, well, the base of this portion of the triangle is 0.3. It's the same over there. So the overall combined triangle is 0.6 inches at its base. Well, there it is. There's the 0.6 inches that represents the base dimension of this triangle. There's the height, 1.7, and it's cubed. Okay, and then divided by 36. Now, it's a little bit of a trick to figure out where the height of the centroid of this triangle is. You probably remember that the centroid of the triangle is 1/3 up from the base. Well, that's 2/3 from the peak, right? So I need a distance 2/3 of 1.7 because I'm measuring everything from the bottom. I've got to be consistent with that. So if you'll notice here, I let Excel do the work for me. I took 2/3 of 1.7. Simple enough. And then the area is just the area of a triangle, base times height over 2. And I don't know why. There we go. So base times height over 2. Oh, easy enough. All these are positive areas. There are other ways to approach this problem. I'll show you a couple of others here in just a second. But that's how I approach this, and that's how I came up with my moments of inertia. Everything else is like any other problem. You just need the distance between the centroid axis. Oh, by the way, the centroid's down here. Take the sum of the AIYI's, get the total area, divide them out, and you've got the centroid, which is at 1.27. It makes sense that it's higher than 1 inch, right? It should be, because we've got more area above than we have below. So, yeah, 1.28 or so inches from the bottom makes a lot of sense. So there's the height of the centroid of that combined shape. And I made it out of 3 rectangles and really 1 triangle. I put 2 halves of a triangle together. Both are obviously, triangles in their own right, but I simply put them together to make everything easier. And of course to show you can do that. So area can be moved around left and right. That doesn't matter. Where you can't move area is away from the axis where you're measuring distance. If you do that, then you change the problem. So back over here, then we calculate the distance between the centroid of the overall shape and the centroid of the individual shapes. Notice I was very careful and consistent, especially on the triangle, to make sure I was measuring to the centroid from the bottom of those legs. So from down here, right, or down here, same thing, that line across there. And then you just have the area area times the distance squared, and then this is just calculating the moment of inertia of each of the areas referenced to the centroid of the overall shape, and then you just add it up, and you've got it. Now I promised you I would show you other ways to do this. Let's cut these and go to some other. So we'll go here. Let me change the size of the figure. And looks like I've got to scroll up a bit. There we go. And I'll paste my shapes because I know I will need them here. Now I've called this one subtractive. So what am I doing here? Well, you notice 2 of the areas are negative. So what am I doing? Well, I'm dealing with a rectangle first of all. And what rectangle is it? Well, it's simple. It's the overall rectangle. 2 times 3, right? So 6, I don't know if these are inches or millimeters or whatever, probably inches. So 6 square inches of area, that makes sense. 2 times 3 is 6. Notice I've inserted a couple of columns here so I could have height and base dimensions and then calculate the areas. Then the location of the centroid of that overall area is just 1 inch up, and there's the AIYI for that rectangle. That's easy enough. The moment of the second area moment for the rectangle is right there, and that's, you've seen it so many times by now you're probably used to it. Well, what are these negative areas? Notice that there's a height of 1.7 and a base of 0.6. To understand what area I'm talking about here, notice that this is just the product of these two times a half. So what are we dealing with here? Well, it's actually easier to see if we go over here. I've divided by 36, so I'm dealing with a triangle here. What triangle is that? Well, the triangle I'm dealing with, it's a negative triangle. I have to resize these a little bit. There's half of it. This might work out better, I think, if I do that. There we go. And there's the other half of it. This is a negative area, right? Now, as I did before, I just take these two, put them side by side. They have the same, despite my drawing here, right? This is crude, but they have a base of 0.3 each, together is 0.6. So you notice I put a base of 0.6 here and a height of 1.7. But now I'm dealing with a negative area. So it's half. I've got this factor of 1/2 because I'm looking for the area of a triangle. Base times height over 2, or essentially times a half. And of course I've got my negative sign because it's negative area. Okay. Now the height of this, well, it's 1/3 up from the base, so I need 1/3 now of the height, and that's exactly what I've done here. It's taken 1/3 of the height. And then the AIYI is calculated. I can calculate the moment of inertia, the second moment of the area. It needs to be negative because this is a negative area. Remember that I'm subtracting from in here from the overall shape. And then just take the base, which is 0.6. Remember I put the two together, so a 0.6 inch base times the height, B3, well that's 1.7 cubed over 36. The last area that I've got here is another rectangle. That rectangle is, if I can move this thing, is of course this negative area right there. Because that's the last area I need to subtract out. So that height is 1.7. The base is 3 inches minus 0.6 twice. So that's minus 1.2, which is 1.8. So that's where the 1.8 comes from. Area is just the product of the two. Of course, I have to add on the negative sign, right? You can't forget that because this is a negative area. The height of the centroid of this is just 1.7 over 2. So there it is. And there's the AIYI. Once we've got the sum of the AIYIs and the total area, we can calculate the ratio of the two to come up with the centroid. And you'll notice this is the exact same centroid we had before when I used 4 areas. It's 1.28, right? 1.28. Calculating the area moment of inertia for rectangles is easy. This is a triangle, so that's why we've got a 36 in the denominator there. And then of course we've got another rectangle here, so another 1/12 BH cubed. But notice that both of these are negative because again I'm subtracting from the second moment of area. The distances are calculated between the individual shapes and the centroid of the overall shape, and then this is again the moment of inertia of each of the shapes reference to the centroid of the overall shape. So we simply add them all up, and you notice we get the exact same answer as before. Consistency is truth, or at least consistency suggests that we've done something right, especially in math. What about the last one? What did I do here? Well, it's the same problem. I just decided to approach it a slightly different way. This was an additive area. Okay, so what does that mean? Well, before I used a 4 area. Remember the 4 areas, each individual leg, the top, and then I used a trick and put the 2 half triangles together into a whole triangle. Okay, they're triangles in and of themselves, but that's what I did, right? What did I do here? Notice I've only got 3. So let's figure out what happened here. We've got a base of 0.6, a height of 2. What would that be? Well, let's see. A base of 0.6 and a height of 2. Well, I believe what I've done here is just put the legs together. Let me show you. So if we take this, like that would make sense, right? So 0.6, except why is it 0.6? Well, it's because notice that there are 2 of these legs, and just like with the triangle, there's really no point in having those 2 legs separate. As far as the area moment of inertia goes, that is equivalent to this. It doesn't matter that one leg's over here and one's over here. These 2 together are distributed about a horizontal line the same way regardless of how far apart they are. It doesn't make any difference. So I'm dealing with this rectangle, a rectangle that represents both of the legs first. And then I've also got another rectangle in here. Should be this one. Yeah, there it is. It's 2.4 by 0.3. What rectangle is that? Well, it should be this one, right up here. Notice I'm being very careful here. I'm lining up, right? Because I still have a couple of areas to deal with that represent the triangles. And I'm afraid I didn't get that square. We'll see if it fits nicely. I've still got these 2 half triangles or triangles that I'm going to put together into a whole triangle, like this. But I needed this to come out right so that it matched that point on both sides. So this would be row 3, where we have a base of 2.4 because it's 3 inches minus 0.6 minus 0.6. I'm sorry, minus 0.3 minus 0.3, so a total of minus 0.6, so 2.4, and a height of 0.3. The y bar is at 2 inches minus half of 0.3, so minus 0.15. That's where I got the 1.85 from. And then it's the same game as before. Calculate the AIYIs, calculate the sum, get the total area, divide the two. We end up with the exact same location for the centroid, the capital Y or the Y bar. And then we just have to use the equation for the moment of inertia of a rectangle through its own centroid here and here. Understanding that this is the two combined legs and this one is the upper, I guess you could call that the lintel or the beam across the top. Then we just need the distance between each of the individual shapes' centroids and the centroid of the overall shape, and we can then come up with the moment of inertia of each of the shapes reference to the centroid of the overall area, and then finally again the total moment of inertia. So you notice we get the exact same results for all of these. It's especially easy to see between these two because the cells are in the same location. So you can approach it any way you want, really. Some ways are easier, some ways are harder, some have more shapes, some have fewer. This one has 3, that one has 3, this one has 4. As long as you're consistent and you are careful, and especially if you're using a subtractive method where you're subtracting out area, be really careful. Make sure anytime you have a negative area that it's a negative area and that its moment of inertia is negative, and then the moment of inertia of that area reference to the centroid of the overall shape will automatically come out negative in the spreadsheet, because if the area is negative, then these terms will also be negative, and so the modifier on the inertia, the second moment of area terms for the parallel axis theorem will be negative, and so the overall will come out negative.